The spectral whisper of the cosmos, the most elusive particle known to science, is undoubtedly the neutrino, a phantom woven from the fabric of reality itself, a ghost that passes through matter with an almost disdainful ease, rendering itself nearly invisible to the most sophisticated instruments humanity has yet devised. To truly apprehend the nature of this enigmatic entity, one must embark on a journey that spans the extreme scales of the universe, from the thermonuclear furnace at the heart of our own sun to the colossal explosions of supernovae light years away, and even into the primordial soup that constituted the universe moments after the Big Bang. The neutrino, initially postulated by Wolfgang Pauli in 1930, a mere placeholder to balance the energy and angular momentum in the decay of a neutron, was so profoundly subtle in its predicted interaction cross-section that Enrico Fermi, upon developing the first theory of its existence, famously quipped that such a particle, if it truly existed, would be harder to detect than the most obscure theoretical construct. Pauli's initial hypothesis addressed the apparent violation of conservation laws in beta decay, where a neutron transforms into a proton, an electron, and this hypothesized neutral particle, which he christened the Little Neutral One. It took nearly 3 decades, until the groundbreaking experiment by Clyde Cowan and Frederick Reyners in 1956, situated near the prodigious power output of the Savannah River nuclear reactor, to finally catch a fleeting glimpse of this ghost, confirming its reality through the detection of the inverse beta decay reaction, a monumental achievement that earned them the Nobel Prize. The sheer elusiveness of the neutrino stems directly from its fundamental properties, or rather, the lack thereof. It possesses an infinitesimally small, but definitively non-zero, mass, a fact that was only definitively established through the revolutionary discovery of neutrino oscillation, an observation that completely overturned the standard model of particle physics in its initial formulation. The standard model, in its pristine, original state, required neutrinos to be massless, traveling at the speed of light, much like photons. However, experiments like Superkamiokande in Japan and the Sudbury Neutrino Observatory SNO in Canada provided compelling evidence that neutrinos produced in one flavor, electron, muon, or tau, could transform into another flavor as they traveled across space. This transformation, or oscillation, is mathematically possible only if the neutrinos possess mass, as the flavor eigenstates are not the mass eigenstates, the quantum mechanical mixing matrix, known as the Pontecorvo-Mochi-Nakagawa-Sokoto matrix, dictates the probability of transformation based on the squared mass differences between the neutrino mass states, delta M squared values, which were precisely determined through these landmark experiments. The current best estimates for these mass differences, derived from multiple ongoing experiments, suggest values in the range of 1/10 of an electron volt squared for one mixing squared difference, and much smaller values for the others, although the absolute mass scale remains one of the greatest unsolved problems in particle physics, with experiments like the Katrin project striving to establish an upper limit, currently placing it below 1 electron volt, a mass so small it is almost negligible compared to the electron mass, which is about 500,000 electron volts. The implications of having a non-zero neutrino mass are profound, extending far beyond the confines of particle accelerators. Cosmologically, the sheer abundance of neutrinos in the universe, often referred to as the cosmic neutrino background, or $text NU $text B $, although vastly harder to detect than the cosmic microwave background, constitutes a significant fraction of the total mass density of the universe. If the summed absolute mass of the 3 neutrino mass states, denoted as $text sum $text M_text NU is large enough, they could constitute a significant component of dark matter, specifically hot dark matter, because relativistic neutrinos would have smoothed out structure formation on smaller scales. Current cosmological constraints derived from observations of the cosmic microwave background by the Planck collaboration, combined with large-scale structure surveys, place an upper limit on this summed mass, currently around 0.1 electron volts, suggesting that while they contribute to the matter content, they are not the dominant form of dark matter, which is believed to be cold dark matter, composed of yet undiscovered, non-relativistic particles. The production mechanisms for these ethereal messengers are as diverse as the astrophysical environments they traverse. Solar neutrinos are perhaps the most routinely observed, born from the proton-proton chain reaction within the solar core, a process where two protons fuse, eventually leading to the production of deuterium, helium-3, and subsequently, helium-4, releasing electron neutrinos in the initial steps. The solar neutrino problem, a historical puzzle stretching from the 1960s until the early 2000s, was the puzzling deficit in the number of electron neutrinos observed on Earth compared to the predictions of the standard solar model. This deficit was elegantly solved not by revising the solar model, but by accepting neutrino oscillation. Half of the solar electron neutrinos were transforming into muon or tau neutrinos en route to Earth, flavors to which the original detectors, such as the Holmes-Take experiment, were largely blind. SNO, by employing heavy water, which can detect all three flavors equally well via the neutral current interaction, confirmed the total neutrino flux matched solar theory perfectly, thus solving the puzzle and validating quantum mechanics in a macrocosmically relevant setting. Beyond the Sun, the most dramatic sources are supernovae. When a massive star, perhaps 20 times the mass of the Sun, exhausts its nuclear fuel, its iron core collapses under immense gravitational pressure in a matter of milliseconds, forming a protoneutron star. This catastrophic collapse releases a staggering amount of energy, roughly 99% of which is carried away by an intense burst of neutrinos. For a few seconds, a supernova emits more neutrinos than all the stars in the observable universe combined emit in photons over the same period. The detection of neutrinos from supernova 1987 text $1 by the Kamiokande 2, IMB, and Baxan detectors provided the first direct, multi-messenger confirmation of core collapse supernova theory. Analyzing the energy spectrum and arrival time of these few dozen recorded events allowed astrophysicists to probe the dense, hot environment of the nascent neutron star, providing critical constraints on the equation of state for supernuclear density matter, a regime inaccessible to terrestrial experiments. Yet, the most tantalizing, and currently unobserved, reservoir of neutrinos are those from the Big Bang itself, the cosmic neutrino background. In the early universe, about 1 second after the Big Bang, the universe cooled sufficiently for neutrinos to decouple from the dense plasma, streaming freely ever since. Due to the expansion of the universe, these relic neutrinos, sometimes denoted as $text NU_text E $text B or $text C nu text B, are now extremely cold, with an estimated average temperature of approximately 1.95 Kelvin, corresponding to energies in the milli-electron-volt range. Detecting these low-energy, nearly stationary particles represents the absolute zenith of experimental physics challenge. Proposed detection concepts, such as the Ptolemy project aiming to trap these neutrinos on a tritium target using extremely sensitive electrostatic traps, or the Tristan experiment exploring novel detection techniques involving high-purity materials at ultra-low temperatures, highlight the monumental engineering hurdles involved. Successfully detecting the $text C nu text B would provide a direct fossil record of the universe when it was merely 1 second old, offering unparalleled insights into the very earliest moments of cosmic evolution, potentially helping to distinguish between competing cosmological models regarding the initial conditions and the number of relativistic species present just before neutrino decoupling, a parameter often denoted as $text N_text F. The mystery deepens when we consider the mass hierarchy problem. The measured mass squared differences suggest two possibilities for the ordering of the three neutrino masses, $text M_1, $text M_2, and $text M_3, either the normal hierarchy, where $text M_1 is the lightest, followed by $text M_2, and $text M_3 is the heaviest, or the inverted hierarchy, where $text M_3 is the lightest, and $text M_1 and $text M_2 are heavier, with the lightest of the three being around 0.04 electron volts in the normal case. and $text $3 being approximately 0 in the inverted case. Determining this hierarchy is crucial because it links directly to the most speculative, yet potentially most rewarding, area of neutrino physics, lepton number violation and the nature of the neutrino itself. This leads us to the concept of the Majorana neutrino. The Standard Model posits that the neutrino, like the electron, is a Dirac particle, meaning its antiparticle, the antineutrino, is distinct from itself, possessing opposite charge and lepton number. However, if the neutrino is its own antiparticle, it is classified as a Majorana particle. This possibility arises naturally if the neutrino has a magnetic moment, or if lepton number is not strictly conserved. The crucial experimental signature for a Majorana neutrino is the observation of neutrinoless double beta decay, often abbreviated as 0 beta 2 nu decay, or $0 nu beta beta $. In this hypothetical process, two neutrons simultaneously decay into 2 protons, 2 electrons, and 0 neutrinos, violating lepton number conservation by 2 units. This decay, if observed, would be the clearest indicator that the neutrino is its own antiparticle, and it would also provide a direct mechanism to constrain the absolute mass scale of the neutrino, as the decay rate is proportional to the square of the effective Majorana mass term, $text $beta beta $. Current experiments searching for this incredibly rare process, such as Gerda, CURE, and the next generation experiment $text candles $, are pushing detection limits to timescales exceeding 10 to the power of 27 years, vastly exceeding the half-life of ordinary double beta decay, which itself is already incredibly long, on the order of 10 to the power of 19 years. The failure to observe $0 nu beta beta $, thus far places stringent upper bounds on $text $beta beta $, indirectly constraining the mass hierarchy. If the normal hierarchy is correct, the neutrino mass scale is likely too low to be detectable by current generation $0 nu beta beta $, searches, demanding even more sensitive detectors for the next decade. Conversely, if the inverted hierarchy holds, the effective Majorana mass $text $beta beta $, could be within the sensitivity window of the next generation of large-scale detectors. The quest for this ultimate confirmation of Majorana nature is intertwined with the question of cosmic matter-antimatter asymmetry. The universe is overwhelmingly composed of matter, a severe imbalance against the initial theoretical expectation of near-perfect symmetry after the Big Bang. This process, known as baryogenesis, requires 3 Sakharov conditions to be met: baryon number violation, $text C$ and $text CP$ symmetry violation, and interactions out of thermal equilibrium. Neutrino physics offers a compelling potential solution through leptogenesis, a mechanism where lepton number asymmetry is generated first, typically through the decay of very heavy, hypothetical sterile neutrinos, which then cascades into a baryon asymmetry via the electroweak Sphaleron process, which violates baryon number conservation at high temperatures. If neutrinos are Majorana particles, they naturally allow for lepton number violation, providing the necessary ingredient for leptogenesis to occur in the early universe, thus providing an elegant, though currently speculative, answer to why we exist at all in a matter-dominated universe. To further probe the mass hierarchy and the potential for $text CP$ violation in the lepton sector, massive terrestrial oscillation experiments are underway. These experiments, such as the Deep Underground Neutrino experiment $text June $ in the United States, which uses a powerful beam generated at Fermilab to send neutrinos across an 800-kilometer baseline to a detector in South Dakota, and its international counterparts like Hypercamia Candae, are designed to precisely measure the oscillation probability over vast distances. By comparing the appearance rates of different flavors between neutrino and antineutrino beams, scientists seek to observe differences in oscillation probabilities, which would be the smoking gun for $text CP$ violation in the lepton sector, a necessary, though not sufficient, condition for leptogenesis. The energy scale at which these oscillations are most sensitive, often in the giga-electron-volt range, allows these experiments to map out the mixing angles within the $text PMNS matrix with unprecedented accuracy, potentially revealing whether the $text CP violating phase, often denoted as $text delta is non-zero. The physics of neutrinos is further complicated by the existence of sterile neutrinos. While the standard model requires 3 active neutrino flavors, each possessing a weak interaction with the $text W and $text Z bosons, theoretical extensions often incorporate one or more sterile neutrinos that interact only gravitationally, hence their designation as sterile. The evidence for a sterile neutrino has been tantalizingly hinted at, most notably by the controversial results from the liquid scintillator neutrino detector $text LSND experiment, which suggested an appearance of anti-electron neutrinos in an anti-muon neutrino beam, implying oscillations into a state that was not one of the 3 active flavors, pointing towards a 4th, sterile state. Subsequent experiments like $text minibu have provided conflicting or null results, leaving the sterile neutrino hypothesis in a state of flux. If sterile neutrinos do exist, they would fundamentally alter our understanding of the neutrino mass structure, potentially acting as the mediators for leptogenesis or contributing to dark matter candidates, depending on their mass scale. A relatively light sterile neutrino, perhaps in the kilo-electron-volt range, could manifest as a distinctive signature in X-ray astronomy, potentially explaining an anomalous X-ray line observed by the $text XMM Newton satellite from galaxy clusters, although this too remains a highly debated topic. The interaction cross-section of the neutrino is the very attribute that makes it the cosmic ghost. At low energies, such as those produced by the Sun or supernovae, the cross-section is exceedingly small, roughly scaling as the square of the neutrino energy times 10 to the power of -44 square centimeters per event per target nucleon. To illustrate this profound lack of interaction, consider a light year of solid lead, an incredibly dense material. A typical solar neutrino passing through this colossal slab of matter would have only a 50% chance of interacting with a nucleus. This weakness is due to the fact that neutrinos only interact via the weak nuclear force and gravity, bypassing the electromagnetic and strong forces entirely. Gravity is so weak at the quantum level that it is completely negligible for particle detection, leaving only the weak force. The weak force is mediated by the massive $text W and $text Z bosons, which impose a very short interaction range, on the order of 10 to the power of -18 meters, explaining the rarity of interactions with the comparatively large protons and neutrons in a detector medium. Detectors designed to catch these elusive particles must therefore be massive, deeply shielded from cosmic rays and terrestrial radioactivity, and often deployed in extreme environments. Deep-sea observatories like $text kilometer 3 net in the Mediterranean, or the IceCube Neutrino Observatory at the South Pole, utilize thousands of highly sensitive photodetectors embedded in vast volumes of ultra-pure water or Antarctic ice, effectively turning the Earth or the ocean itself into the detector medium. IceCube, for instance, utilizes a cubic kilometer of ice, an unprecedented volume, to achieve the necessary target mass to capture a handful of high-energy astrophysical neutrinos, those originating from distant blazars or active galactic nuclei, which arrive with energies reaching peta-electron volts, or 1,000 trillion electron volts. These high-energy neutrinos act as messengers carrying information unimpeded by magnetic fields, unlike charged cosmic rays, providing a cleaner view of their distant, violent origins, a field termed astroparticle physics or multi-messenger astronomy when combined with gravitational waves and conventional electromagnetic observations. Looking forward, the next decades promise a potential revolution in our understanding of the neutrino sector. The precise measurement of the $text C-text P violating phase $text delta by $text June and $text hyper K could confirm the necessity of the majorana nature for leptogenesis, bridging the gap between particle physics and cosmology. Simultaneously,
The dedication of experiments like $text Tristan and $text Senior to the search for the $text C new text B could unlock a direct probe of the conditions prevailing at the 1 second mark of the universe, providing crucial cosmological parameters. If the sterile neutrino hypothesis is validated, it would necessitate an extension of the Standard Model, potentially introducing new symmetries or interactions that could also shed light on the nature of dark matter. The enigma of the neutrino, the spectral whisper of the universe, encapsulates a central tension in modern physics: the profound success of the Standard Model in describing 3 of the 4 fundamental forces, contrasted sharply with the inescapable evidence that this model is incomplete, primarily because of the neutrino's mass and its mysterious flavor oscillations. From Pauli's desperate scribbling on a napkin to the kilometer-scale instruments buried in ice and water, the pursuit of the neutrino has forced physics to confront its own boundaries. Whether the neutrino remains a mere 3-flavor quantum field excitation or transforms into a major inner particle that holds the key to baryogenesis, its elusive nature ensures that it will continue to dictate the direction of fundamental research for the foreseeable future, remaining the most subtle, yet perhaps the most cosmically significant, particle in our inventory. The final chapter of the neutrino story is yet to be written, awaiting the next fleeting interaction, the next faint flash of light across kilometers of matter, that will finally give substance to this universal ghost.